Okay, we are now on the second queuing model, which is Md1 queuing. So for this, the assumption of exponential distributed times between the arrival of successive vehicle, which has boson arrival, in some cases give a more realistic representation of traffic flow than the assumption of the uniformly distributed arrival times. So therefore, the Md1 queue, which has exponentially distributed arrivals, deterministic departure, and one departure channel, has more important applications within the traffic field analysis. For Md1 queue, we have another term that we have to define, which has traffic intensity. Traffic intensity actually is denoted by rho, and that is equal now to the ratio of the average arrival to the average departure rates. So our rho refers to traffic intensity, that is unitless. Our lambda is the average arrival rate in the vehicles per unit time, and mu is the average departure rate in vehicles per unit time. So if we're going to assume here that our rho or traffic intensity is less than 1, so we can have our queuing performance equations for our Md1 queue. So we have here the average length of queue in vehicles denoted by bar q equal to rho squared over 2 minus 2 times 1 minus rho. Our average waiting time in queue, which is bar omega, is equal to rho all over 2 mu times 1 minus rho. And our average time spent in the system denoted by bar t is equal to 2 minus rho all over 2 mu times 1 minus rho. So we have to take note that it is important to note that under this assumption that your traffic intensity is less than 1, wherein average arrival rate is less than the average departure rate, the DD1 queue will predict no queue formation. So, however, a queuing model that is derived based on the random arrivals or departures, such as the Md1 queuing model, will predict queue formation under such conditions. So, we have here our problem. So, for our problem, consider the entrance to the recreational park that was described in the previous example. However, let the average arrival rate be 180 vehicle per hour and Poisson distributed exponential times between arrivals over the time period from park opening time, which is 8 a.m., until closing at dusk. Compute the average length of queue in vehicles, average waiting time in the queue, and average time spent in the system. We assume a Md1 queuing. So for this one, we identify that our arrival rate is 180 vehicle per hour. This is for all T, which means that from the opening at 8 a.m. until closing, the average arrival rate is 180 vehicle per hour. And our average departure rate per vehicle it took 15 seconds. Based on the previous problem, it took 15 seconds to distribute the brochure. So that is now the departure average departure rate, which is 15 seconds per vehicle. So let us try to convert this one into minute. So for our arrival rate, that will be 3 vehicle per minute for all T. Then our departure rate is 4 vehicle per minute for all T. Now we can have the value for our traffic intensity, that is the ratio between our arrival rate over our departure rate denoted by rho. So that gives us 0.75. To compute now for the average length of queue, we make use of the equations that we have presented a while ago. So we start with the average length of queue denoted by bar q. So actually the formula here from our previous one, that is rho squared all over 2 times 1 minus rho. You simply have to substitute the value for rho, and it gives us now our average length of queue, which is 1.125 vehicle. Now for the average waiting time in the queue, bar omega. The formula to this, of course, is rho all over 2 mu times 1 minus rho. So which means that we simply have to get the substitute the variable, the specific value, then we get now 0.375 minute per vehicle. And the last one, of course, is our average time spent in the system. So that is the queue time plus departure time. So that is bar T. The formula to this is 2 minus rho all over 2 mu multiplied to 1 minus rho. So simply have to substitute the value for rho and mu. So we get here a value of 0.625. So alternatively, actually, because the departure time is 1 over rho, so we get a 0.25 minutes it takes the park attendant to distribute the brochure. So therefore, we can have this equation. We can have this equation that average time spent in the system will be equivalent to the average waiting time plus the departure time, which is 1 over mu. If we try to substitute now the values, we get also a value of 0.625 minute per vehicle. So this is just an alternative solution for getting the value for the average time spent in the system. Still, they have of the same value. Now we move on to Mmn queuing. A queuing model, this queuing model assumes that one departure channel and exponentially distributed departure times in addition to exponentially distributed arrival times. So this MM1 is applicable in some traffic applications. So what is an example for exponentially distributed departure? So it can be applied to toll booth where some arriving drivers have the correct toll and can be processed quickly, while others do not have a correct toll and produces distribution of departure about some mean departure rate. So our MM1 assumption can be shown that the following queuing performance equations can be applied. So we have here our queuing performance equations. You have our average length of queue in vehicles. We have our average waiting time and the average time spent in the system. So for this one, if you're going to have an example, assume that park attendant takes an average of 15 seconds to distribute brochures. But the distribution time varies depending on whether park patrons have questions relating to park operating policies. Given an average arrival rate of 180 vehicle per hour, compute the average length of queue, average waiting time in queue, and average time spent in the system. So we assume here we're going to use Mmn queuing. So for this one, we have average arrival rate, which has 180 vehicle per hour, and the average departure rate is 15 seconds. However, that average departure rate, which has 15 seconds, that distribution time may vary somehow, which is dependent on the questions that the driver may ask or may raise to the park attendant. So there will be a variation on the time distribution. So dependent on the park patrons if they have questions regarding to some park operating policies. So for this one, if we're going to have our average arrival rate, the departure rate, and traffic intensity, if we're going to make use what we have computed in the previous discussion, wherein our average our traffic intensity, we're going to make use traffic intensity was, as previously computed, is 0.75. So we're going to make use this average traffic intensity rho so that we can compute for the average arrival rate. So that is to get our average length of queue. So the average length of queue denoted by bar q is equal to rho squared all over 1 minus rho. So we're going to make use 0.75 as computed previously in our problem. So it gives us now 2.25 vehicle. Now for the average waiting time in queue, so we're going to have here that will be equivalent now to the value here is rho. So we just have to substitute our value, which is now equivalent to 0.75 minute per vehicle. Then the average time spent in the system, so we're going to have our equation over 4 minus 3. So we got here a value of 1 minute per vehicle. So of course, for our equations, we make use of our computed mu a while ago, which is our mu is 4. Our mu here, we have to take note, the mu is 4. The average rate is 3. This is now converted to minute. So we simply have to substitute this value to the formula that we have presented a while ago, wherein we have here our equations. For this one, this is rho squared all over 1 minus rho. This one is, the formula is lambda all over mu times mu minus lambda. And this one, the formula here is 1 all over mu minus lambda. We simply have to substitute those value for our mu, which is average arrival rate. Our mu is average departure rate. Our lambda is average arrival rate, and our rho is the traffic intensity. So now after we substitute, you get now the value for our average length in queue, average waiting time, and average time spent in the system. Now we move on to Mmn queuing. So this is a more general formulation of the Mmn queue is the Mmn queue, where n is the total number of departure channel. So Mmn queuing is a reasonable assumption at toll booth or at toll bridges. So wherein there is one departure channel available, more than one toll booth that is open. So for this can also be applicable to parking lot, where n is being the number of parking stall in the lot, and the departure rate mu being exponentially distributed times of parking duration. So for Mmn queuing is also frequently encountered in non-transportation application, such as checkout lines at retail store, security checks at airport, and so many other applications. So the following equations here describe that operational characteristic of Mmn queuing. We have to take note that unlike for the previous queuing model Md1 and Mmn, which requires that the traffic intensity rho be less than 1. So this one, the equations allow rho to be greater than 1, but apply only when rho all over n, which is our utilization factor, is less than 1. So we have here the equation wherein we have our equation, probability of having no vehicle, probability of having n vehicle in the system, and of course the probability of waiting in queue time. So if we're going to have the probability of having no vehicle in the system, we have this equation. So this is the equation, probability of no having a vehicle in the system, the probability that then the probability of having n vehicles in the system, you make use of this equation. Then we have our probability wherein for our probability of waiting in queue, so we have here in the equation. So the probability of waiting in a queue, you have this equations. So you have to take note that our n is the number of vehicles in the system. That is small letter n. Our capital letter N is the number of departure channel. Our n sub c, departure channel number, and rho is the traffic intensity. And of course, we still have our equations that to be used. You have our average length in queue. You have the average waiting time in the queue and the average spent time in the system. So you're going to make use of these equations.